Hi, hello everyone. This is our lecture 11, and we are going to talk about support vector machines. So we are going to start with linear classifiers, then we are going to move to support vector machines, and finally we are going to see the kernel trick. We have already discussed the kernel trick when we talked about kernel reach, and here we are going to kind of look at this concept again. The references are these papers and this book by Vapnik, and the papers are both of them are on our Google Drive. Okay, so let's kind of refresh a little bit what we saw in the previous lecture. So how can we go from logit and probit to other classifiers? Okay, and here I'm thinking again about a two-class classifier. Okay, so we saw previously that when we have a dependent variable y that takes values on the set 0, 1, the goal was to model the conditional success probability. So the probability of y being equal to 1 given a set of covariates, right? And basically, we assume a functional form for these probabilities that we call g, and this g function is, of course, nonlinear, that it will map a set of covariates that takes values on the reals to the interval, the closed interval between 0 and 1. Okay, so the argument of this function g is linear, so it's given by x prime beta. Okay, and with this argument we use this function g to map the regressors into the 0, 1 space. Okay, and we basically consider two choices of function g. The first one is the probit model, where g is the cumulative um, distribution function of the normal random variable, so there's no g here. Okay, and the one of the most common choices for the function g. The other possibility is to take the logit CDF, which is expressed by this ratio of exponentials. And usually the vector of parameters beta have to be estimated by maximum likelihood. And if we are in large dimensions, we can use like penalized maximum likelihood with ridge penalties, lasso penalties, elastic net penalties. So basically all the penalties that we have studied so far can be applied to this maximum likelihood problem. Okay. And then when we map into probabilities, we have to move from probabilities to the decision, to the classification. Okay. So in this case, we define a threshold or cutoff point, and if the probability, the estimated probability given by the function g of x prime beta hat is larger than this threshold c, then we classify this specific observation as belonging to class 1. And if it's less or equal to C, then we classify as belonging to class 0. Okay? And today we're going to look into more general classifiers. So the support vector classifier is based on covariates, okay, and also on covariates, and in its most simple form, it's also a linear classifier. But we are going to see by the end of this first block that we can transform it into a nonlinear classifier in a very nice way, and somehow it's also simple way to move from a linear classifier to a nonlinear classifier. Okay, so we have n pairs of x and y's. Okay, and we want to separate the y's into two groups. Okay, and here for convenience, instead of labeling to the two classes 0, 1, we are going to label the two classes -1 and 1, and it will be clear why we do that. But basically, we are going to look into a different cost function, and that will naturally can be naturally written when you have classes -1 and 1. We basically are going to look into the probability of correct classification. Okay, so this classifier is very effective if the dimension of X is much larger than N. Okay, and so it's well designed to high dimensional problems. Okay, and of course we are going to look into the math behind it. Okay, and it's an interesting alternative to read your lasso. Okay, and in the second block of this lecture, we are going to like do a step back, and we are going to borrow the ideas from the support vectors, which is a kind of a methodology design for classification problems, but we are going to borrow these ideas and we are going to revisit the regression problem, and we are going to apply these ideas to regressions. Okay, and we are going to look at the support vector machine regressions. Okay, and this will be another alternative to the set of tools that we have already studied. All right, so we have the covariates, we have the outputs that takes values either 1 or -1. We have a training pairs, okay? And we want to know a nonlinear classifier, okay? We want to learn or estimate this unknown function f naught that maps the x's into these two classes, okay? 1 and -1, okay? And then if we get a new point, a new data point, we want to classify this new observation as being -1 or 1, okay? Which class this new observation belongs. Assuming that we have only the x's, but we don't have like the labels, we don't have the y's, okay? So simple classification problem. We have apples and pears, and we want to classify the fruit if it's an apple as a pear. Okay, so you have like two cases. On your left, it's very simple. You have like the two sets separate way. So to the left, we have the apples. To the right, we have the pears, and it's clearly separated into two groups. On the right panel, so it's a more complicated problem because apples and pears are kind of mixed together. Okay, and so how can we classify these things? So we are going to take a very simple approach. Okay, so we are going to look to classifiers that will be the sign function of a possibly nonlinear mapping of x. Okay, and this g function here that we see here, okay, is mapping the covariates into this binary output 1 or -1. Okay, if a classifier is linear, then the function g is given by w prime x plus b, where W's are the weights and B is called the bias. Okay. Thus, the linear classifier will be given by the sign function of this linear argument. Okay. So basically, we are split into classes with a hyperplane divided by. So we are going to divide the classes with a hyperplane defined by W transpose X plus B. Okay. So this is kind of in a two-dimensional case. It's clearly that here we have the apples and the pears linearly separable. So we have this hyperplane which in this case is a line, and this orange line that's defined by the equation w prime x plus b equals to 0. Okay, and we have the apples on one side and the pears on the other side. Okay, and if we have a new variable, a new individual, we classify them just applying the sign function to w transpose x new plus b. So the method would just tell on which side of the line this new observation lies. Okay, but then big question, how we choose the hyperplane. Okay, and so it will be great to have a hyperplane that separates the inputs with label 1 from the inputs with label -1, making no classification errors, right? So in such case, that's why we define as -1 and 1, because we can look at this term here. So if this equation means that if we have the correct classification, so if y is 1 and f is 1, the product will be 1. If y is -1 and the function is -1, then the product is also going to be equal to 1. So this is saying that we are correctly classifying all the observations, okay? So, and we are going to use this expression here in order to find like the optimal, the best hyperplane. Okay. So in 2D, in 2 dimensions, of course, the discrimination is a line. Okay. So here, clearly a line splitting the space into 2 subspaces, where on one side you have the apples, on the other side you have the pears. Okay. If we are in 3 dimensions, so you have like apples and pears living, fluctuating in these 3 dimensions, the splitting, the decision split is a hyperplane. See, there's a hyperplane that will divide the space into 2 subspaces, 2 3D spaces, where on one subspaces we only have the apples, and on the other subspace we only have the pears. So in this case here, the separation is crystal clear, so we are not making any classification error. Okay. So we can say that the points are linearly separable if there exists a hyperplane defined by W and B, okay, such that W transpose X plus B will be positive if Y equals to 1, and W transpose X plus B will be negative if Y equals to -1, okay? Of course, some data points are not linearly separable, uh, and we are going to look into that a little bit later, but let's first consider the case where we have data points that are linearly separable, okay? The problem is that even if this is the case, that we are in this simple situation, uh, which hyperplane should we choose? Maybe there are many possibilities that split this correctly, split the observations into these 2 classes. Okay, so how we define a criterion to find a single separating hyperplane? Okay, so this is kind of a situation. So here on the top we have linearly separable, but and then we have the hyperplane, but we can also have here a hyperplane like that. It also splits the data into 2, or we can have a hyperplane like this, and these are all a separating hyperplane. So we have to define which hyperplane we are going to use, okay? And of course, the bottom panel, we don't have linearly separable, and we have to find a way to could linearly separate these observations. Okay. So again, here is the possible hyperplane. So this is a possibility, this is a possibility, this is a possibility, this is also a possibility, this is also a possibility. Of course, this one is not a possibility. But among these 5 hyperplanes that are possible solution, which one should we choose? Okay. So to answer this question, we're going to define what we call the support vectors, and we are going to start by defining the distance from a point X to a plane defined by the W and the B. Okay, so the distance between the point and the plane is the ratio of the absolute value of W transpose X plus B and the norm of the vector W. Okay. In the next slide, we're going to prove this expression, exploring some geometry of the Euclidean spaces. Okay, so here we can see why that expression is true. So here we have a 2-dimensional space. Okay, the green line here defines the hyperplane that's defined by this expression. Okay, so we have a point here, x naught, lying on the hyperplane. Okay, and this vector w star is just the vector w divided by the norm. So this is a unit vector, so it has norm, this vector here has norm equal to 1. Okay, and we have here another point, general point x. Okay, so the distance between x naught, which is a point lying on the hyperplane, and this point x is given by this red line here. Okay, so the norm of this vector in red here is the distance. Okay, so we know that for any point x naught in this hyperplane, okay, we have W transpose x naught equal to minus B naught. Okay, this is by construction, this is because of this expression. Okay? So then we can easily show that the distance between x and x naught will be given by W star transpose x minus x naught, which is exactly this expression here. Okay, so the expression can be easily computed just by exploring the geometry, and it's easy to show that in 2 dimensions. So this is the expression of the distance. Okay, so now let's define what we call the support vector, the positive support vector and the negative support vector, that will be defined as belonging to the argument that minimizes wx such that y equals to 1 and x minus be the argmax of wx such that y equals to minus 1. Okay, so since we have that x prime x plus b define the same plane as c as a constant c, the constant different from 0, if we multiply the expression, the hyperplane equation by c, we are defining exactly the same hyperplane. Okay, so we may normalize the support vector such that w transpose x plus b equals to 1 and w x minus plus b equals to minus 1. Okay, so we're going to define these 2 extreme cases that are defined here. So we have here one support vector and another support vector. So it defines the frontier. Okay, so this support vector is such that we have this expression here true, and these are another one. This other support vector here, this one here, is defined by this expression. Okay, so this is a kind of extreme case because you have some observations lying exactly on the top. Okay, so if we move this support vector, for instance, the black one to the left, we are going to misclassify some apples. Okay, so it's exactly the right hyperplane. If we just move it a little bit to the left, we make classification. We have classification errors. The same thing with the pairs. The purple one. If we move to the right, a little bit to the right, we are going to misclassify some pairs. Okay, so we define like this extreme hyperplanes. Okay? And we can define the margin exactly. It's the distance between the two hyperplanes as defined here. Okay, and now think for a second. If we have large margins, it means that the apples and the pears are very clearly separated into two regions. Okay, when we have narrow margins, it means that apples and pears are very close to each other on the boundary of this decision frontier. Okay, so they are very close to each other. So maybe there is a region that's not where the classification is not at all that clear. Okay, so large margins means classification is much easier than narrow margins. Okay, so we want big margins. Okay? That's what we want. If we have big margins, then classification is better, right? So for a given W, okay, we can again compute the margins is 2 over the norm of W, okay? And we want to maximize the margin while respecting the normalized constraints. Okay, we want correct classification. Bear this in mind. So we want to keep Wx plus b larger or equal to 1 if y is positive, and Wx plus b less than minus 1 if y is negative. It's minus 1, okay? And this is a key for avoiding overfits, that larger margins are more robust, okay? Because classification is more crystal clear, okay? So this is a kind of an optimal hyperplane. Okay? So how we would do that? So we can solve, it's an optimization problem with restrictions, right? We can solve this optimization problem where we are maximizing the margin subject to the constraints, to the correct classification constraints. Or we can write this in another form, like minimizing the inverse of the margin subject to the constraint that y wx plus b should be larger than 1. Okay. So this second one, this second optimization problem is a quadratic optimization problem and is subject to n linear inequality constraints. Okay, and if a solution exists, then it's unique and it's called the optimal hyperplane. So that's the way we are going to find the optimal hyperplane. Okay, and how can we solve that? Okay, so basically we write the Lagrangian. Okay, so we are going to look at this function L that will be 1/2 x at w prime w minus the n constraint multiplied by the Lagrange multipliers that are defined by the alpha terms. Okay, and we are going to derive the first order conditions, and by the Karushkin-Tucker theorem, um, uh, we can find a solution, okay, with positive multipliers, okay, and this solution will be optimal, okay, and this will imply a complementary slackness, okay, that for every I, so for every sample point, we have that alpha I times the restriction will be equal to 0, okay. Uh, so for every Y that the constraint is inactive, okay, so such that the restriction Y times the linear function is larger than 1, we are going to have an alpha I corresponding Lagrange multiplier equal to 0. Okay. So this on your slide you can see the first order condition. So it's the derivative of the Lagrangian with respect to W and with respect to B. Okay. And then we can easily find that the W will be given by the sum of the product of these three terms, the Lagrange multiplier, the Y's, and the X. Okay. And also we have another restrictions that the weighted combination of Y's and where the weights are given by the Lagrange multiplier should be 0. Okay. And we can plug the first condition back in the Lagrangian and use the second one to rewrite a function W of alpha that will be given by this expression that you see on your slide. And we solve for alpha by maximizing this dual problem, subject that the alpha must be positive, and the restriction that the linear combination of y's where the weights are given by the alphas is 0, okay? And the complementary is slackness condition here, okay? Therefore, if we define the alpha naught as the maximizer of the previous function, W of alpha, okay? And then the solution, the optimal hyperplane, is given by this function, okay? And for every I, okay, alphas are positive only for the support vectors, and will be 0 for all the other points, okay? So the optimal hyperplane is given by W naught transpose X plus B naught, and this is the expression of the classifier. So this is a linear support vector machine for data that are linearly separable. Okay. Important question: what if the constraints are never satisfied and the solution does not exist? If the constraints are never satisfied, it means that the data set is not linearly separable, so you have to introduce some nonlinearity, okay? Or we allow from some crossover, some misclassification error, but then how much is enough? And this will, of course, that depends on how you penalize misclassification in the training data, okay? So one thing that we can do, we can introduce some non-negative slack variables denoted by xi, so xi1 to xi n, and modify the constraints. So instead of the previous constraints, we write this way. So we introduce the slack variables here, okay? And for the slack variables large enough, we can always fulfill the constraint, okay? So this is what we call the soft margin classifier. So here we have clearly a misclassification point. And with the slack, so now we have a different constraint optimization problem that now we have this additional term in our minimization, and note that also the linear restriction, the linear restrictions are now modified. Okay, and C is a regularization parameter that's positive. Okay, so C equals to 0 means that we could pick psi equals to infinity, and all the constraints are automatically satisfied. A small c means that we allow some crossover. Large C means little crossover. Okay. C equals to infinite means psi equals to 0, and we are back to the original problem of no crossover, what we call the hard margin. Okay. So if a solution exists, then it's unique, and it's called the optimal hyperplane with soft margin, or the optimal generalized hyperplane. Okay, and the constraints are given now by this expression, okay? And we can like define the size as the maximum between 0 and the kind of classification error, okay? And the problem then becomes an unconstrained minimization problem where we can solve for this expression here, okay? And basically, if we set lambda equals to 1 over 2 times the number of observations times c, we can define this loss function here, and the problem looks like a ridge regression. Okay, so we are penalizing the squares of the and we have a different loss function that is given by this expression. Okay? So it looks like a ridge. And this loss function is called the range loss, okay? And that's what I'm just said, that includes a kind of a ridge type regularization, okay? So these loss functions penalize misclassification points, take into account the distance of, sorry, of x to the correct hyperplane. Okay? All right, but can we do better than that? Can we avoid classification error at all? So let's take this example here. Okay, so you have like orange points and blue points. Okay, and we want to separate both. It's clearly that we cannot do this linearly. Okay, but imagine now on your minds that we can, with some magic, okay, we are looking at these 2 points, orange and blues, on a 2 dimension. Imagine now that I have the power to take away the orange points. Okay, so now we transform these, instead of a 2 dimension rectangle, we transform this in a kind of a cube. Okay, and we attract the orange points in our direction, but we leave the blue points on the screen. So we have the blue points on the screen, and we have the orange points fluctuating here. So if we do that, we can put here a hyperplane dividing the two, right? So that's exactly what we can do. So in this case, I attracted like the blue points and I kept the orange points there. So here we can have a hyperplane splitting the two set of points, and in this case, um, the points are linearly separable. Okay, so here what we did, we apply a kind of second order degree polynomial transformation to the variables, and we now have a different set of variables. Instead of working on R2, we are working to the R3. So now our covariates are x1 square root of 2 times x1 times x2 squared. So now we have, like, instead of 2 attributes, we have like 3 attributes to split the hyperplane. Okay, and that's the trick. So the support vector machine consists on 2 steps, the general support vector machine. We are going to map the input x into a high dimensional expanded feature space Z using a nonlinear transformation phi that we are going to choose a priori. Okay, and then we are going to find the optimal separating hyperplane in this expanded feature space. Okay, so step 2 is exactly what we have discussed so far. So it's linear separation. Okay, so the trick is how to move from a low dimension space into a higher dimension one. Okay, so why should we worry about step 1? Because after the transformation, separation should be evident. Okay, so that's the key thing. So the expanded space, we have classes that are linearly separable. Okay, so support vector machine in its general form is kind of a nonlinear separation device. Okay, so imagine here we have like 2 classes. Okay, the reds and greens. Okay, of course they are not linearly separable. If we try to fit a linear support vector, that's what we get on the dashed line and the margin defined by the black lines. We cannot correctly separate. Okay, but imagine now that these points are on a rubber surface. Okay, they're on this rubber surface. Okay, of tablecloth, and we can bend and we can twist and we can stretch this rubber surface. Okay, so what we are going to do, we are going to take the extremes. Okay, here, and we are going to bend here. Okay, so if we take a piece of paper, okay, it's like we're going to try to do something like this. Okay, so you're going to move from this to that. Okay, so this is kind of the movement that we are doing. We are putting down the extremes related to the red dots, and we are going to moving up the extremes and with the green dots. Okay, so this is kind of the transformation that we are making with this rubber surface. Okay, look at that. So you can see now that we moved in this new space. Now we have, like, we move from 2 dimensions to 3 dimensions. Okay, and now we have the red points on the bottom of this space and the green points on the top of this space. And we have a hyperplane here, this guy here, okay, this hyperplane here, separating these the two classes perfectly. It's linearly separable. Okay, so That's the trick. Okay, let's see another example. A line. We have a line in one dimension. We have again greens and reds. Of course, these points are not linearly separable. But again, we have this rope and we can move in all directions. So we first are going to do this. Now we move from one dimension to two dimensions. Okay. Are the points linearly separable? No, right? We cannot solve the problem in two dimensions because we have, unfortunately, we have these points here, and with a single hyperplane, we cannot correctly split these regions. Okay, so we need one dimension more. So we are going like to again to transform this into that, and now we have in this three-dimensional space, we have the green points on the top, and again, the red points on the bottom. And voila, we have the separating hyperplane, okay? So we have this hyperplane that's perfectly separating the reds from the greens, okay? This is the kernel trick, to move from a low dimension space to a high dimension space. So in the first example, we move from 2D to 3D. In the second example, we move from 1D to 3D. Okay, so in both cases, we need three dimensions to correctly separate the classes with a linear classifier. Okay, so how should we transform the variables x? How you should the transformation phi? Okay, so basically, if we have a linear classifier, that's our optimal hyperplane. We can define the alphas, so no problem. But instead of applying these to the x's, we are going to apply these to the transform variables, right? So this is our optimal classifier, optimal linear classifier. Okay. So it depends only on the product yi, yj, xi, xj. Okay. So it depends on the inner products of the x's. Okay. So we are going to work with that and transform these inner products. We are going to work with the inner product. Remember the kernel trick that I showed you when we talk about kernel ridge? It's exactly what we are going to do here. Okay, so we have this transformation phi of x that we are moving to a d-dimension space to a k-dimension space. Okay, and now we have data that's y and the phi of x. Okay, and from the previous slides, our optimal hyperplane now will be defined by yi, yj, phi xi transpose phi xj. Okay, because we have this new set of variables. Okay, so the optimal classifier depends only on the inner product of this expanded space. Okay, and that's what we are going to work with, basically using the Mercer theorem. Okay, and the Mercer theorem says that the continuous symmetric function k of u and v describes an inner product in some feature space if and only if k of u v is positive semi-definite. Okay, so in principle, this theorem is telling us that we do not need to worry about finding the right transformation directly. We can work with the inner product. So basically, we define this function k that will be given by the inner product of phi xi, phi xj. Okay, and so this function k is denominated the kernel. Okay, and the function phi is denominated the kernel eigenfunction. So we have many kernels, kth degree polynomial, Gaussian radial bases, Laplace radial bases, neural networks, and many, many possibilities. Okay, the very first example that I gave to you was with the kth degree polynomial. Okay, so this is an example of a kernel. This is another example of a kernel, and this is another example of a kernel. See, and the idea is that, for instance, here if we make this transformation, you want to have like points here, here, and here, and here belonging to one class, and points on the bottom belonging to the other class, such that you can trace a hyperplane that splits the data. If you have more complicated data, you can use like this, the Mexican hat, where you have the top of it one class and the other classes around it. Okay, or even more complicated like this, like some waves. Okay, and so basically, how we go from the kernel to the transformation. So as Mercer's theorem says, the kernel is defined by the inner product. So the idea is to factorize the kernel to identify the transformation. So for second degree polynomial, that's what we have. Okay, but we don't have to care about that. Just if you want like to see which are the transformations, but the only thing we need is the kernel. So you define the kernel, and then you can find the support vectors, and you can find the separating hyperplane. Okay. So so we can decompose the kernel. So if we have a polynomial kernel, we're going to have a polynomial basis function. Okay. And how? But in practice, which kernel? It's more experimental. You have to try different kernels and see if you are correctly classifying or not correct classifying. You have to look at the classification error. So there's no much guidance here. So it's more like a trial and error in practice to see which fits your data better. You can even use cross-validation to look over cross-validation sets, which kernel is performing the best. Okay. Uh, so that's exactly what I told you. Okay. So that's our first block. On the second block, we are going to discuss support vector regressions. The third block is an application. I'm not going to record any videos. We are going to discuss the third application during our live session on Friday. Okay. Thank you very much. See you soon.